In Chapter 12, we're going to be studying statistics. Now, statistics is the practice of collecting and analyzing numerical data. So sometimes it's not feasible for us to study the whole entire population for certain characteristics or just to find out some information. So instead, we use what's called a sample size, a smaller portion of the population. Now, depending on the outcomes that we come out with for studying the sample, we can use this data to make inferences about the entire population. So 12.1 is going to start us with sampling, frequency distribution, and graphs. Population versus sample. A population in a statistical study is an entire group of individuals about which we want information. A sample is part of the population from which we actually collect information used to draw conclusions about the whole or the entire population. A random sample is a sample obtained in such a way that every element in the population has an equal chance of being selected for the sample. When we talk about equal chance, that reminds me of when we worked with probability and rolling a die. Each side of the six-sided die has equal chance of occurring. So the same thing with our sample. Each person in the population, for instance, would have equal chance of being selected. They have an example listed here as rate my professor, which students use to rate their professors, and other students are allowed to go through and read about the student's experience with a certain professor. Again, it's randomly done. Also, another example would be maybe in class, I may have students count off starting with the number 1 and going to number 4. So students would count 1, 2, 3, 4. Each student would take a number, and I would randomly select, for instance, the students with the number 4s to come up to the board and work a certain problem. Again, I'm just randomly selecting the students. I'm not directly choosing each student. Construct a frequency distribution for the data of the age of the maximum yearly growth for 35 boys. So we have 35 boys represented in our data. No specific order on here, just 35 boys with specific ages there. Notice that the smallest or lowest age is 10 and the highest age is 18. So this is listed on our frequency distribution table. First column, age of maximum growth. We start right here with number 10 and we're ending with number 18. Now what we do next is we go through our data set and we calculate how many boys are in each age group. So for age 10, we only have 1 boy. For age 11, we have 2, and so forth. If you add the frequency up, or the column, you should get a total of 35, and that means you have accounted for each of the 35 boys. So this little table or chart you have is called a frequency distribution table. It shows the age plus the frequency. This next slide is going to help us create a frequency distribution table. So we start out with telling statistics. These are test scores listed as our data set. And notice what we have in the very first column. These are called test scores by class. So I'm just going to list numbers by these so I can make a quick reference. This is class number 1, 2, 3, 4, 5, and 6. Now to create the tally marks, what we do is we look at each data value. So the first one is 82. And I go to the class where 82 falls within that interval, which is class number 5. And I put a little tally mark representing 82. We'll go grab the next data value, 47. 47 falls within class number 1. Again, I'll put a tally mark representing 47. Now we do this for each of our data values. Go completely through your data set, and then we add each tally mark and make a frequency column. So the frequency column, the number 3 here, represents how many tallies we have listed in that first class. All right, and again, what you're doing is you're creating a frequency distribution. You have your test scores in the far left column, and then the right-hand side, you have the frequency, and that is your frequency distribution. So using the information from the maximum yearly growth on a previous example, where it gave us the maximum growth of the boy's age and then the frequency for each age, we can use this information to create what's called a histogram. Now, you notice on the histogram, there are vertical bars and they are touching. So you need to make sure when you do a histogram, you want to touch. Why are we making a histogram? We're making a histogram because sometimes in a presentation, if you show someone just this frequency distribution chart, it doesn't make sense. It's not as clear what this data is representing. Whereas if you look at the histogram, you can tell the peaks and lows of what age. So therefore, sometimes it's easier to read or look at something graphical. So this is an idea that you can use is to create a histogram. All right, so what happens is we have the age on the horizontal axis here, and then the number of years or the frequency is listed on this vertical axis. All right, this little bit of a tilde inside there, that's called a break. That's just telling you we're not starting at age 0 because it wouldn't make sense to start there. All right, that is just this little dent in our line. All right, so we start with age 10 and we go up to age 18, and notice the height of age 10 is a 1 right here. All right, the height of age 11 matches the frequency, that is a 2. All right, and we just do that for each one of these. The height of the bar represents the frequency. And you can tell by looking at this histogram that the maximum yearly growth seemed to hit its peak at age 14. Using the frequency histogram for the same data we just looked at, boys' ages of maximum yearly growth, we can create what's called a frequency polygon. So you can see our green bars, that is our histogram. And at the top of each bar, there is a point. And I'm not sure if you can see this, I'm putting a little blue dot at the midway point on the top of each bar. All right, and then we also would start where we would have the number 9 on our graph, except for we're not going to place it because that is not on our data set, and 19. So you want your polygon to start at the x-axis and connect all the dots until you create and come back down to the x-axis at the 19 mark so that you create what's called a frequency polygon. Then you take your frequency polygon and you can just use this for your presentation. So depending on what you're presenting, sometimes the histogram is more effective in relaying what you're trying to interpret, and sometimes the frequency polygon may be your choice. Again, we're just giving you different ways to present your data. A questionnaire was given to students. The first question asked was, how stressed have you been in the last week on a scale of 0 to 10? And with 0 being not stressed at all and 10 being as stressed as possible. The responses are shown to the right. So we have our first column, which gives us our stress rating, 0 through 10. And then we have the frequency, the number of people that responded with that specific rating. All right, our question number 1, or A here, says, which stress rating describes the least number of students? So when it says least number of, you're looking at the frequency. So for the frequency, we'll look for the smallest number. Again, the smallest number means the least. And so we notice it's a 1. All right, let's read that question one more time. It says, which stress rating? So it doesn't want the frequency. It wants you to use the frequency to find the stress rating. So this case here, the smallest number is frequency of 1, and it refers to stress rating number 2. So the answer on here would be 2 out of 10. All right, for part B, it says how many students responded with this rating. So that would be our number 1, the frequency of 1. Part C, which stress rating describes the most students? So again, on this one, we're looking for the highest count on the frequency. So this is the highest frequency, or the most. And this refers over to the stress rating of 8. So which stress rating describes the most students? That's the stress rating of 8. How many students responded with this rating? And that is 27 responded with the rating of 8. A professor has students keep track of their social interactions for a week. The number of social interactions over the week is shown in the following grouped frequency distribution. Identify the lower limit of the 5th class. All right, identify the lower limit of the 5th class. So they numbered the classes just like we did previously. This is class number 1, number 2, number 3, 4, and this is the one we want, class number 5. All right. The class lower limit is going to be 60, and then the upper limit is 64. So since they want the lower limit, we would insert 60 into our answer. Again, lower limit is 60, upper limit is 64. So the number on the left is lower, the number on the right is the upper. All right, and for the next question, it says that we're still looking at the same frequency distribution. How many students had at least 70 social interactions for the week? So in this case, what we're looking for is how many had greater than or equal to 70 interactions. Greater than or equal to means 70 and above. So if you notice on the last 4 classes that we have 70 here, starting as our lower limit. And we need to add all the classes that follow because they have above 70 interactions. So we'll take each frequency for each of those last 4 classes and add them together. 6 plus 7 plus 0 plus 1 will give you a frequency of 14. So it says how many students had at least 70 social interactions for the week? That would be 14 students. Students were asked, how stressed have you been in the last week on a scale of 0 to 10? With 0 being not at all stressed and 10 being as stressed as possible. All right, so we have our frequency distribution given below. Instead of it being vertically aligned like we're used to, it is horizontally aligned. So it says construct a histogram and a frequency polygon from this data. So what we need to know about the stress rating, this is going to be our x-axis. And the frequency is going to be our vertical up and down on the left-hand side, our y-axis. All right, so once again, this is my x and this is my y. So make sure that you have the frequency listed on the vertical rise there on the left side. All right, and what I like to do on this one to figure out our histogram, we know our histograms, the bars all have to touch, no spaces between them. I will go ahead and select just this first rating. The rating of 0 has a frequency of 3. So I'll look at each of these histograms they have below. I'm looking at the 0 rating, and it should have a height of 3. So if we look at this first graph, it has 0, and look where we're at. It has a height of possibly 15 there. So that is too tall. I'm going to delete that as an option. Same thing with the one right below it. The bar is raised above 3 for that rating of 0. So I'm looking at these 0 ratings. So that's not going to work either. And you can see that on this third one here for 0, it doesn't even have a height at all. So therefore, that leaves me with the 4th option to choose. And that would be my histogram. All right, and then once again, if you were to put a dot above each bar and connect the dots and bring it back to the x-axis, that would create your frequency polygon. So it's hard to tell that I'm doing this, but That's kind of the image of your frequency polygon, and the closest one we have again is going to be this third option. Again, you can look at where the rating is 0 and see if the height is 3 and try some different values on there and just check each one. Remember, the tallest one that we have is this rating of 7. It has a frequency of 32. So where we have a rating of 7, that should be the peak or the highest point. You can see on this first one here, it doesn't quite get there to that 32. All right, so a process of elimination to help you answer these problems. We have seen how to use the frequency histogram and the frequency polygon to display data. Now in this case here, we have another option. We use what's called a stem and leaf plot. All right, so we're going to use the same information we had before. This is statistics test scores. This is for 40 students. And to create a stem and leaf plot, what I like to do is start out with what's called a key. So a key is kind of like a legend. It tells you what it means to have that separation of these numbers. So for instance, I'm going to grab the first number, 82, and I'm going to say 82 is equal to the presentation of 8 with a vertical line and the 2 on the right-hand side. So the 8 on the left side is my stem. The 2 on the right-hand side of the vertical line is a leaf, or the ones position in this case. All right, so again, looking at 82, I'm going to go to my stem that has the 8, and I'll place the leaf, the number 2. If I go to the next number, 47, I'm going to go to the stem that is a 4 and place the 7 as the leaf. And we'll do this for each of our data values until we have all of them listed. Again, stem and leaf plot is another way to display your data so that you can take a look at it and make some inferences or make some conclusions or make a statement about your data set. All right, so for instance, we can make a comment about the 70s here since it has a lot of values, right? So we can say that we had a lot of C's, a lot of values in the 70s. If we count the number of C's that we have 11 grades that are in the C's out of 40 students. So we can say approximately 25% of the scores scored a C on this test. So just for an example of what you could do. Now, once again, let's remind ourselves of what this means. So for the stem of 4, this is representative 47, 45, and 43. But it's written as a stem is 4, the leaves are 7, 5, and 3. And this is an example of a stem and leaf plot. All right, for this problem, it says a random sample of 40 college professors is selected from all professors at a university. And it gives you the following data of their ages. All right, so this is the age of 40 professors at selected university. It says determine the leaves for each corresponding stem. Complete the table below. See if I can give myself a little more room here. So they started us out with 2. And what you do is you look at your number, your data sets, what is the highest number you have? And I believe we go all the way out to the 60s. So we'll have 2, 3, 4, 5, and 6. Those would be our stems. All right, so to get started, what we can do is go and identify all the numbers in the 20s. And let me see if I can find them. There's 1. All right, so I think I've found all of them. And what I can do is I'm just going to place them order. My leaf for 28, my leaf is 8. And notice it says use a comma to separate the answers as needed. So there's my 8, comma. My next one is 29. My leaf will be 9. Next to my data set is 21. My leaf will be 1. And lastly, 1. And again, you're going to go through all of your data, have it represented on your stem and leaf plot. So I'm just getting started with this one, and I'll leave that for you to finish. So using the information from the previous slide about the 40 professors, we've created this stem and leaf plot that you see now on this slide. And that part A was to create the stem and leaf plot. Part B is right here. It says, what does the shape of the display reveal about the ages of the professor? So let's read each of these carefully. A is none of the college professors lived to be 70 years old. All right, it didn't say anything about survival or living, so that's not anything that we would be looking at. B is if you are younger than 30, you cannot be a professor. And you can see that we have some professors in the 20s, so that is not the case either. C, the greatest number of college professors are in their 40s. So if you take a look at our STEM, and definitely we have a majority listed in their 40s. And D is none of the above. The only one that is true would be your choice C. So once again, we're using a stem and leaf plot to help us answer a question. For this slide, we need to describe what is misleading in the visual display of data below. So they're already telling us something is wrong. Let's read the title. Percentage of the world's computers in use by country. All right, they give us a key, the little box that has colors in it. It says country A is 29%, country B is 4%, and so forth through each of the color-coded countries. Then we have a circle graph, or you can consider it a pie chart with the different various colors on there. All right, it says choose the correct answer. It says the title does not explain what is being displayed. Well, that's not true. The title is stating what is being displayed. The chart is too small. Well, in this case, yes, the chart's too small, but normally when you have a key or a legend, it is going to be smaller than the actual data value that's being graphically shown. C, the colors on the chart are too light and distort the data. They're definitely not light colors. They're very bright colors. And D, the percentages do not add up to 100%. So let's take a look at that. We can add these percentages up. We have 29 plus 4 plus 4 plus 5 plus 6 plus 9. I don't know, maybe this chart is too small because it was really hard for me to see. And then if we add this up, what you're going to find out is these are not going to be equal to 100. So I believe this is 57%. My goodness, that's not good. So therefore, since it's not equal to 100%, it is deceptive, right? So we're going to choose D as our answer. Another thing that you can tell just by looking at it, look at country A, and it says right here that it is 29%. If you look at the red, which is country A, on the circle graph or the pie chart, it looks more like 50%. So how can we say this is 29% when it's coloring half of the circle? All right, that's my question mark. Doesn't look right. So that is a bit of misleading, or not even a bit, a lot of misleading of the chart. So be careful when you look at your graphics. Make sure they make sense. Deceptions in visual displays of data. So let's read the title. Percentage of people in the United States living below the poverty level for the years 2001 to 2005. All right, and so we have our distribution information, our data information right in the center there. It has the years 2001 to 2005, and it has the rating of the poverty level. Now, each of those graphs are showing the same data. All right, they look really different, but they are about the same because they're showing the same data set. So let's take a look at the one on the right. If you look at the one on the right here, we have a line. It's not quite horizontal. It is slowly increasing, and then it looks like it levels off. So my question is, does it really level off? We're not sure. What you need to focus on this graphic is the fact that they have all their data values between 11% and 13%. There's a lot of wasted space above where there's no data, and there's a little bit of wasted space below where there is no data. So what would be a better idea is to zoom in between 11 and 13% so that you can get a better depiction of what this data is telling you. So we'll take a look at the first graph. And the first graph, notice they're starting at 11.3%, and it goes all the way out to 12.9%. So this data set is focusing on 11% to 13%. And if you take a look at this image here, you can see that in the year 2001, we're at 11.7, and you can see we are steadily increasing for the first 4 years. And then from 2004 to 2005, we decreased just a little bit. All right, so you can see a better depiction of the data set that there is a very big increase in the poverty rate versus that first graph we looked at, which doesn't look like there's much of a change. All right, so you want to be careful when you look at your data sets. When you create them, does it say what you need to say? Does the image truly show everybody in your audience what you're trying to relay to them? If it's not a good visual image, then again, there's going to be some deceptions or misunderstanding as to what you're presenting. All right, so this concludes our lecture on 12.1.